Okay, thank you. I'd like to thank the organizers, including the technical and administrative staff. And I want to thank Hubert for inspiration, which I think I hope will be visible in this talk. So actually the subtitle of the talk could be trying to answer a question that was asked by Hubert in the 1980s with the help of hints that were dropped by Hubert in the years 2000. So this work emerged from, in the context of a collaboration with Hubert, together with also Jesper Jacobsen, Ranveram Nives-Vivat, and Linnea Grant-Samuelson. They're all here. So the main aim of this collaboration, maybe long-term aim, is to actually solve the critical ON model in 2 dimensions. And where do we start? I mean, we should start with the spectrum, the space of states. So for today, my aim is to say something about the structure of this spectrum. So this ON model, as its name indicates, has a ON symmetry, a global symmetry, in addition to the conformal symmetry, because it's a 2-dimensional conformal field series. So it has a conformal algebra, which is the product of a left-moving and right-moving Virasoro algebras. It can be defined as a loop model, and you obtain the CFT by taking the critical limit. So the problem that I want to address is to write this space of states as a representation, or as a combination of representations of the conformal algebra and of the global symmetry group. So I will focus in particular on the global symmetry group, which is the orthogonal group ON, where the number n is actually allowed to be any complex number. First I probably have to say what is the group ON with n complex. Well, actually, it probably doesn't make sense, but it doesn't really matter for the ON model, because as a lattice model, you can define the lattice model in such a way that n is a parameter, as was shown, I think, by Yassin Niklev. So n is a parameter. I mean, you can try to take it complex. Well, probably you cannot give any complex value, otherwise the critical limit may not exist. But at least you can take a critical limit if n is between -2 and 2. And afterwards, you get a CFT, and you can analytically continue this CFT to any complex value of n. So let's say we allow n to be any complex number. So now we want to exploit the ON symmetry. So we don't really need an ON group for n complex, but we certainly need ON representations. We need to know representations, and in particular, the tensor products. Unfortunately, that makes sense for any complex n. So the idea is that you can, of course, define them for integer n, and then you can send n to infinity. And if you do, for example, a tensor product, you have multiplicities there, which are integers. And if you send n to infinity, well, the multiplicities increase, and then they stabilize, and they have a finite limit. And that limit should be interpreted as the multiplicities for the tensor products of ON representations with n complex, actually. And so if you want really mathematically safe explanation of all this, you can turn to the recent paper by Binder and Ryzhkov, if you like category theory in particular. But yeah, for physicists, we can just accept these basic facts about representations. So where do we start to determine the spectrum? Well, let's start with the partition function, which was already determined in the 1980s by Hubert, together with Philippe Di Francesco and Jean-Bernard Zuber. So the partition function, which I write as Z ON of Q, well, it's a function of n and Q. It's a torus partition function, and Q is a geometric parameter of the torus. And it is written here as a combination of characters of the conformal algebra. So these chi are characters of the conformal algebra. And they come in 2 series. So one of them is, I would call a degenerate character, chi s of q. And the other one, chi rs of q, is an even simpler Verma module character. Eta of Q here is the Dedekind eta function. And really the non-trivial structure here is the momentum PRS. So PRS is a momentum indexed by two numbers R and S, which in the spectrum take fractional values. PRS also depends on beta, which itself is related to n. So by the formula, n equals -2 cosine pi beta squared. And then in this formula, in addition to character, in the partition function, you have multiplicities. This dRs of n, these multiplicities, well, we'll consider them in more detail later. I'm just giving the formula so that you know that we know them explicitly in principle. They are given as some kind of Fourier transform of Chebyshev polynomials. So P here, I'll define it later precisely, it's a kind of Chebyshev polynomial. So therefore, we already know the partition function. So the question is whether we know the spectrum. So what does it mean to infer the spectrum from the partition function? Well, here I'm rewriting the partition function, and below I'm trying to rewrite it in terms of a spectrum, meaning a space of states. And I want to write the spectrum in terms of representations. So representations of On. So this empty square bracket is the identity representation of On, the singlet representation. Then we have lambda Rs, which are other representations which I want to determine, but which are not known for the moment. And we also have representations of the conformal algebra. So R, S is, and W, R, S are two series of representations of the conformal algebra. And from the partition function, we get some information on these representations. So for the On representations, we get their dimensions. I mean, the multiplicities dRs of n, which appear in the partition function, should be the dimensions of these On representations. And on the conformal side, we have the characters of these representations. So the characters, by definition, are traces of Q to the power L0. So there's a typo here. It should be L0, the generator of the Virasoro algebra. So now, if we were in a Virasoro minimal model, we could essentially deduce the spectrum from the partition function, because we would assume the representations are irreducible, and then if you know the character, you know the representation. But here in this model, in the On model, you can't do that. You can't really assume the representations are irreducible. Actually, if you do that, you end up with conformal blocks that diverge. So you have to look for more general representations with the same character. And actually, there exist infinite series of representations with this character chi Rs of Q. So I will briefly review this part of the story before focusing on my main topic, which is the On representations. So, well, the first series of representation, Rs, is actually easy. It's just a degenerate representation. So the problem starts with WRS. Well, not all WRS are difficult, because if the indices R and S are not both integers, then there is no ambiguity. It has to be a Verma module. But if the indices are both non-zero integers, then we have null vectors in the representation. And a null vector, it may either vanish or not. And it gives you the possibility to build more complicated representations, in particular logarithmic representations. So in our case, there is infinite family of representations which have the character chi Rs. So for WRS, we have this infinite family of choices. And we have to find a way, well, extra information beyond the partition function to determine which one is the correct representation. And this has been done essentially last year by two different methods, actually. So one method was to use the existence of degenerate fields to constrain the spectrum itself. So if you have degenerate fields, typically you have differential equations, BPZ equations for correlation functions. But actually you also have constraints on the spectrum, and And this has been used for a long time, in particular in logarithmic conformal field theory. So since we have here degenerate representations, so we have degenerate fields, and basically we can use that to reduce the problem of finding WRs to WR0, because the degenerate fields can shift the last index, the index S. And WR0 itself is not degenerate. It has no null vectors, so its structure is basically known. And it allows you to find the structure of WRS as well. And the other method, as was mentioned by Yifei He in her talk today, is to just take the critical limit of the lattice model. And there is also a nice story here with the logarithmic feature emerging in the critical limit while it's not present at finite size. And it converges on the same structure for the logarithmic representations. And if you're still not happy with that, to check it all, we could bootstrap some 4-point correlation functions which test these results on structures of representations, because if you know representations, you can compute conformal blocks, and then you can write crossing symmetry equations and look for solutions of crossing symmetry. And if you have the wrong blocks, typically you don't find any solutions. Okay, so that's it for a very quick part of the problem, the part about representations of the conformal algebra. So now I'll move on to the looking for the correct representations of the ON group. First, I have to give a quick review of what are representations of ON. And if you want basic mathematical information like that, where do you look? Well, typically you have a look in Wikipedia in case the information is already there. And if you do that 1 year ago, you don't find it. Well, you can find some information on representations of Lie algebra in general, for example. But with ON is a bit more special. It's a classical Lie group. It has a parameter n. So you want these results in a form that makes the dependence on n explicit and simple. And so to do that, you have to use a specific construction of these representations, Veil's construction. And so well, you can find it in the mathematical literature, but it takes some time. And so now it's in Wikipedia since I wrote the corresponding article. So what are then the irreducible finite dimensional representations of ON? Well, they are parameterized by Young diagrams. And their dimension is given by a polynomial in n. And this polynomial is written here. It's a factorized polynomial with integer roots. So let me explain a bit the notations for this formula. So notations are explained in the picture below, in the picture of some Young diagram. So here the Young diagram is written as 8, 5, 5, 4, 2. So 8 is the length of the first line, the number of boxes in the first line, 5 in the second line, etc. So here, if you look at the third line has 5 boxes. So that's called lambda 3, number of boxes in the third line. Lambda tilde are numbers of boxes in columns. And then if you have a box, like the box 4,2, which is in red, you have the hook length, h lambda of 4,2, which is the number of boxes on the right or below that red box, including the red box itself. So given these notations, you can understand in principle this formula for the dimensions of representations. And so you can start applying the formula, computing dimensions of representations, and comparing them with the multiplicities that you find in the partition function. And so if you do that, well, let's start with the representation 1. So 1 between brackets is just the vector representation of ON, and its dimension is n, of course. And it happens to coincide with the multiplicity d1/2 0 of n, the first non-trivial multiplicity in this partition function. So that's nice. You want to say the representation, lambda 1/2 0, is just the fundamental representation. And it works well also if you look at lambda 1 0, which has multiplicity 1/2 n plus 2 n minus 1, and which therefore coincides with the symmetric 2 tensor, 2 between brackets. It works also for lambda 1, which is the antisymmetric 2 tensor, and lambda 3½ 2/3 has to be the representation 2, which is neither fully symmetric nor antisymmetric tensor. Now the problem starts if you look at lambda 3½ 0, which according to its dimension could be 2 possible representations. It could be the combination of 3 plus 1, 1, 1, or it could be 2, 1 plus 1. And these ambiguities get worse as you increase the indices. They get much, much worse. And yeah, of course, you don't expect from the dimension of representation to be able to determine the representation. You need extra information. So where would this extra information come? Well, the very useful hint comes from the open spin chain. And here we are going back to work done by Hubert SALEUR and Nick Reed in the 2007, which was already mentioned in Jesper's review talk. So the idea is that our ON model is supposed to be the critical limit of a closed spin chain. Now, a closed spin chain has not necessarily very nice properties when you tensor the representations that appear in the spectrum, because if you want for the spin chain, you would have to cut it open and merge it with another closed loop, maybe, to form a larger loop. And if you cut it, you could break some symmetry. But if you have an open spin chain, you can just take 2 chains and join them by their ends. And so what they notice is that you have nice properties when you tensor the representations which appear in the spectrum of the open spin chain. But there's a relation between the open and the closed spin chain. Basically, the open spin chain representations, which I denote as lambda r, are just sums of the closed spin chain representations over the last index. Yeah, I'm not sure if Hubert approves this way of rendering his work, but that's heuristically maybe one way of understanding it, why the open spin chain here has simple algebraic properties. So the simple algebraic property is this lambda 1½ tensor with lambda r gives lambda r minus 1½ plus lambda r plus 1/2. So a simple SU2 tensor product rule, if you want. And due to this rule, I mean, if you know the first representation lambda 1½ you can deduce all the others by repeatedly tensoring it. And one way to write the result is that, okay, we have the dimension of the lambda r, which we know from the partition function, which is P2R of n. And we have the representation lambda r, which is given by the same polynomial, P2R of 1, of the vector representation. 1, which is also lambda 1/2. So here, P2R is a Chebyshev polynomial. Well, it's a modified Chebyshev polynomial because here in its recursive definition, I'm starting with 2. To have a true Chebyshev polynomial, you have to start with 1, but it's just a minor rescaling. And then the main recursion relation for this polynomial is just this relation, which is the mirror, if you want, of the SU2 tensor product rule. Okay, so we know this representation lambda r from the open spin chain, and the trick to obtain them, if you know their dimensions, is just to replace n with some representation of dimension n. Well, there is only one representation of dimension n. It is the vector representation. So could we use this in the closed spin chain, or if you want, in the CFT? Well, let's try to do that. So first I'm rewriting this drs of n, which is the multiplicities, which are supposed to be the dimensions of these representations lambda rs. And it is written in terms of the same Chebyshev polynomial. So here, if you want, it is a sum, it is a kind of Fourier transform over the index of the Chebyshev polynomial. And the indices of this Chebyshev polynomial P in this formula are 2r wedge r prime, which means the greatest common divisor. And then the argument of the polynomial is n. So for example, the first few polynomials, well, P1 is n by definition, P2 is n squared minus 2, etc. So why not just take this formula for the dimension and replace n with the vector representation? Well, if we do that, I mean, it fails immediately because, for example, for D11, you get what is written here, 1/2 of 2 plus 1, 1, minus 1 plus the singlet. So basically, you don't get a representation at all. What you get is a kind of formal representation. So a combination of irreducible representations, but with coefficients that can be fractional and that can even be negative. So that's not really the solution. However, maybe we can keep the idea, but what we don't want actually to replace n with a true representation in our formula for DRS of n. We could replace n with a formal representation. What has to be a true representation is lambda RS itself. So we have to look for formal representations whose dimensions are n. And to do that, let me introduce alternating hook representations, which are some formal combinations of representations with coefficients that can be 1 or minus 1. So that's why they are alternating. So for example, the 5, 5 would be, well, I wrote 5, 5 in two notations. So one of them is the diagrams here. And above, you have the notation with the brackets. And you have then the general formula for this series of alternating hook representations, phi t, where, for example, you have t minus k, 1k, which means a first line with t minus k boxes, and then k lines with just one box. So, and the non-trivial statement about these representations is that indeed their dimension is always n, as you can in principle deduce from the general formula for dimensions of representations. And then why not then insert these representations phi t inside the formula which is reproduced below for the dimensions. Well, basically, every time we have an n, we have to choose which alternating hook representation we insert instead. And the correct choice is to insert it so that the product of the index of the polynomial, P2R wedge R prime, with the index of the representation is constant. So here, therefore, I'm inserting a phi whose index is 2R over 2R wedge R prime. And that's because when you start tensoring these representations, essentially the number of boxes add. And you want to build lambda RS, you want to combine a number of representations which all have basically the same maximal number of boxes. Okay, so now we have an ansatz for the representation lambda RS. Well, I'd like to make it into a conjecture. So to call it a conjecture, I first have to check that indeed lambda RS is a true representation. A combination of irreducible representations whose coefficients are positive integers. So to do that, we can take this ansatz and compute it for the first few cases. And in particular, for the case lambda 3/2 0, it resolves our ambiguity. I mean, based on just the dimensions, we had two possibilities for lambda 3/2 0, but now we are selecting one possibility. Okay, then for the other representations, we check that the coefficients are positive integers. We have little to compare them with, except some isolated result by Gorbenko and Zahn, who actually, they really wanted to know if there was a singlet with the dimension delta 2, 0. So they looked at the limit n goes to 2, and in that limit they could determine the structure of lambda 2, 0, basically. And they find this structure, which is reproduced by by our conjecture now. So now we can push further. Well, it becomes, of course, more complicated. Maybe one feature of these representations I'd like to point out is that the multiplicities start increasing. For example, if we look at here for lambda 3, 1, we have a multiplicity 5 already for the ON representation 2, 1, 1. So the meaning is that in this space of states, we have 5 different states which all have the same conformal dimensions and which also transform in the same way under the global symmetry ON. Okay, so since this works, basically, we get positive integer multiplicities, we can say that our formula for lambda RS is really a conjecture, which might be taken seriously. Now the challenge is to test the conjecture, and well, that's already the outlook. So we are presently testing the conjecture, so by bootstrapping 4-point correlation functions. So here maybe I'll explain quickly what this has to do with ON symmetry. Because a priori, the crossing symmetry equations that Yifei here explained today, for example, in the case of the Potts model, well, these equations are written in terms of conformal blocks, which are objects deduced from the conformal symmetry and which know a priori nothing about the global symmetry. However, if you know how the fields transform with respect to a global symmetry group, you can predict the numbers of solutions of crossing symmetry equations. And for example, in the Potts model, well, the 4 connectivities that Yifei talked about, they are 4-point functions of the type, well, phi 1/2 0. And now this field, phi 1/2 0, in the Potts model, well, in the Potts model, the global symmetry is the symmetric group, SQ. It's not the orthogonal group, but the story is still very similar. And so this field, phi 1/2 0, it transforms in the fundamental representation of the symmetric group, which is also labeled by this Young diagram with just one box. And then we know that the tensor product of this with itself as a representation of the symmetric group is given by, well, the symmetric 2 tensor, the antisymmetric 2 tensor, the fundamental itself, and the identity representation. So basically, we have 4 terms here, and that would be the algebraic explanation why you have 4 different connectivities. I mean, the space of solutions of crossing symmetry for this 4-point function has dimension 4, basically. In ON, the things are a bit different because in ON, the same tensor product, well, gives you only 3 representations. You have still the 2 and 1, 1, but you also have, you don't have anymore this 1. Basically, in ON, you have a conservation of the number of boxes modulo 2. And so for the corresponding 4-point function in the ON model, we expect to find 3 solutions of crossing symmetry, and that's what we find, actually. Well, actually, in many other examples of 4-point functions, we find the number of solutions predicted by this by this action of global symmetry. However, it doesn't work in every case. I mean, in other cases, we find actually fewer solutions than we would have expected based on ON symmetry alone. And well, we should not be too surprised because actually, as already predicted by Reed and Saleur, the global symmetry of that model is not really ON. It's larger than ON. So since we have a larger symmetry, I mean, some of the solutions we would expect based on ON symmetry might be actually not independent due to the larger symmetry. And this larger symmetry also, I think we need it if we want to solve the model, because as we saw, if we decompose the spectrum into representations of conformal algebra and of ON, we get multiplicities which are non-trivial and which quickly increase. And to tame all this multiplicity, we'd like to distinguish the different fields by the action of some larger symmetry. Yeah, and then we are also working on a similar story for the Q-state Potts model, where we have a similar conjecture for the action of the symmetry group SQ on the space of states. Okay, thank you for your attention.
Thank you very much.